All right, so this is going to be a video about a related rates example problem. And basically the problem is going to be stated as follows. It says you are inflating a spherical balloon at a rate of 7 cubic centimeters per second. How fast is its radius increasing when the radius is 4 centimeters? So the first thing I'm going to do here is draw out a picture of what this looks like. And that's generally step one when solving these, is just kind of draw a picture, at least make a mental picture of what this looks like. So I'm going to do my best to kind of draw a balloon here. All right, so we got a little circle right here, and then it's got a string here. So there's our circular balloon, okay? And it says that it's inflating and it's increasing at a rate of 7 cubic centimeters per second. So you have to kind of imagine it's increasing in all directions at a rate of 7 cubic centimeters per second. Okay, so I'm gonna actually just write that on here. It's increasing 7 cubic centimeters per second. Now, it's important to know that cubic centimeters are volume. So if you think about this 3 right here with the cube here, you just got to think 3-dimensional. So it's increasing at a rate of 7 cubic centimeters per second. Now, that's important to know that it's the rate and not the actual volume. The volume is not 7 cubic centimeters. It's the volume's rate is increasing at 7 cubic centimeters per second. Okay, so it's a change. It's a rate. It's the rate at which that balloon is increasing its volume. Okay, then it's asking how fast is its radius increasing. So I'm going to just draw a little picture of the radius here. So this is just a circle here, and then, or it's a sphere, and then this is the rate. This would be the radius right here, r. And then it's asking for how fast is the radius increasing if the volume is increasing this fast when it's 4 centimeters. Okay, so basically I'm gonna rewrite all of these instructions basically, and I'm gonna basically translate them into math. Okay, so it says that the rate at which the balloon is being inflated is 7 cubic centimeters per second. So I'm gonna actually write that as dV over dt. Now the reason why I'm doing this is because it's the change in volume over the change in time, okay? The rate of the volume changing with respect to time. It's equal to 7 cubic centimeters. So I'm gonna write equals 7 cubic centimeters per second. Okay, it's really important to make sure you write down dV over dt. Don't just write V is equal to 7 cubic centimeters per second, because then that's going to lead to some problems. Okay, it's really important to note in the problem what each thing means. So if it says rate, that's really important. You're going to want to have a d over dt, and that whatever variable, in this case it's volume, would go right here. So d over dt is generally going to represent the rate. So I'm going to kind of write that over here. Anytime you have d over dt, it's going to represent the rate. Okay, and then whatever you're doing the rate of is basically going to go right here. So we're finding the rate of the volume with respect to time. So the rate of the volume is 7 cubic centimeters. So we're not actually looking for that. This is just given in the problem. Okay, then it says how fast is its radius increasing? If you notice, it does not say what is the radius. It's asking for how fast is the radius increasing. That's another tip basically that you're looking for a rate. So how fast is the radius increasing is basically saying how fast is the rate of the radius changing. Okay, so I'm going to write dr over dt. Okay, that r stands for radius, and the d over dt again means rate. So the rate of the radius changing, and I'm just going to write equals question mark because we actually don't know what that is. That is what the problem is asking for. So step 2, again, back to the translating everything from English to math, is to write down everything that you possibly know that's given here. In this case, what we're looking for, I'm just going to put a question mark since it's not actually given. Then it says how fast is it when the radius is equal to 4 centimeters. So I'm just going to write at r equals 4 centimeters. Okay, so this is trying to be an at. So when the radius is 4 centimeters, how is the radius changing? How fast is the radius changing? Given the fact that we know that the balloon is inflating and changing its volume at 7 cubic centimeters per second. Okay, so that would be step 2. Step 1, draw a picture. Step 2, translate everything that's given into math. Okay, so now it's all in math terms. Okay, step 3 is to create an equation or use an equation that relates this volume and this radius. So any variables that you have, in this case v and r, you need a formula or an equation that that combines those two and shows how they are related. That's why it's called related rates. We have a rate here and a rate here. We have to show how they're related. In order to do that, we need an equation that has them both related. In this case, it would be the volume of a sphere. So I'm going to write the volume of a sphere equation right here. So volume of a sphere is equal to 4/3 pi r cubed. Okay, that's usually given to in any of the problems, or you just have to kind of memorize what the formula is for that specific equation. So we know that the volume of a sphere is equal to this, but what about the change in volume? What's the rate of the volume changing? In order to figure out what that dv over dt is, you are actually going to have to take the derivative of both sides of this with respect to t. So I'm going to write dv over dt here. So I'm taking the derivative of this volume of the sphere, and then I'm doing d over dt here to find this side as well. So if you take the derivative with one side with respect to t, you have to equally do that to the other side. Okay, so on the left side here, we are going to have dv over dt. Okay, equals, okay, now you have to do the derivative of this right here, and this involves implicit differentiation. Okay, this 4/3 pi, we don't really need to worry about it because it's a constant, but we need to do the derivative of this r cubed with respect to t. So in order to do that, you should notice that it's a power, so because it's r to the third power, so we're going to bring this 3 down. So it's going to be 4/3 pi times 3, that 3 is going to be brought down based on the power rule, r squared, okay, because you minus 1 from the power. Now the r and the t don't actually match. So if you remember our implicit differentiation rule, you have to multiply by whatever that variable is divided by whatever it's with respect to, okay? So it would be dr over dt like this. Okay, I'm going to simplify this expression a little bit with this 3 over 3. So that's going to basically cancel out, and you're left with 4 pi r squared. So I'm just going to kind of rewrite this really quick. Okay, now from here, we're basically going to just be filling in everything that we know, because there's certain variables that we know. In this case, we know dv over dt because it's right over here. Okay, 4 pi r, well, 4 pi is just constant. We know the r, in which we're like looking for right here because it's this 4 centimeters right here. And then we're solving for dr over dt, as you can see right here. So everything is linked. We know everything. We just need to kind of substitute everything in here. Okay, so dv over dt is going to be equal to 7 cubic centimeters per second. So I'm actually going to write that down, 7 cubic centimeters per second. It is important to write the units in there. Some people kind of don't worry about the units so much because the units are all the same. In this case, we have centimeters here and centimeters here. So the units don't necessarily change themselves, but I'm just going to put that in there just in case you ever do see a problem where you are going to need to change the units around. So 7 cubic centimeters per second is equal to 4 pi. Now it's times r squared. The r that we're looking for is 4 centimeters. So I'm going to write 4 centimeters in here. And then it's squared times dr over dt. Okay. Okay, now from here, I need to solve for this dr over dt, so we're solving for this. So we need to get rid of this whole thing right here. So I'm basically going to be dividing both sides by what this is. But first what I'm going to do is actually simplify this. So I'm going to rewrite it really quickly. Okay, this right here is going to be 4 squared, so it'll be 16 square centimeters. So I'm going to write that in there, 16 squared centimeters, dr over dt. So things are simplified a little bit more here. Now from here, I'm going to divide both sides by this 4 pi times 16 squared centimeters. Do the same thing to this side, 4 pi times 16 square centimeters. Okay, now from here you should notice that this centimeters cubed divided by centimeters squared, it'll actually cancel out 2 of those, and then both of these will cancel out as well. So you're only left with centimeters squared on this side, which makes sense because our unit for the change in radius over change in time is going to be centimeters per second. Okay, this is going to cancel out. Okay, now from here, it's basically just plugging this into your calculator. Okay, from here, it's just basically plugging it into your calculator. This is a 16. Okay, so you just throw this in your calculator, and you should get about roughly 0.0348 centimeters per second is equal to the rate at which the radius is changing. Okay. So that would be the final answer for this given problem. Now in my class, I stress on the fact that if it's a real world problem, you are going to be rounding. You're not going to keep things in terms of pi or in terms of radicals or anything like that. So do make sure that you do round accordingly to whatever the teacher says if they want you to actually do that. In my case, I usually do 3 or 4 decimal places, but it really doesn't matter as long as you kind of get close to what the number's supposed to be. We're not really going to worry about sig figs too much. So that's basically an example problem of related rates. If you have any questions about anything in this video, let me know.